Hey, what's up, everyone? Welcome to the final episode of Mr. Lewis Speed Runs Your Homework. Um, this time we're going to be looking at homework 1.5, this one right here. Let's do it. Oh, buddy, we're given a graph this time. Oh, jeez. Oh, no, what are we going to do? Alright, let's take a look. Let's break it down. So, the graph here is showing the speed of a ball rolling down a hill for different amounts of time. Use the graph to answer the following questions. So we can see that our dependent variable, or measured outcome, is speed in meters per second. We can see that our independent variable is time. So we can see that the ball is, as time increases, the speed increases. Okay, and that's also highlighted here in the positive slope, right? So positive slope means it's pointing upwards. Okay, so the independent variable, which is the independent variable is always the x-axis. So independent variable here is time. It is measured, the symbol for it is given right there. It's that little t. And its units are seconds, which is what's in parentheses. Dependent variable, speed, symbol is v. And units are meter. Whoa, bruh, what happened? No, don't mark it. Oh my goodness. Alright. And units are meters per second. Okay. The slope of the line is 3.07. And the y-intercept of the I don't know why I keep scrolling. The y-intercept is 4.15. Okay, the equation okay, so it's saying swap the equations, or swap the symbols in the equation. So instead of using y and x, use t and v. Okay, so the y values, y is replaced by the symbol from here. Y equals m is slope, which in this case is 3.07, times x is speed, which is little v, plus b, which is 4.15 here. How long does it take to reach 22 milliseconds, or meters per second, sorry. That's going to be hard for me to see, because I don't, my computer's far away from my face. So you could look at this and try to be like, okay, so it's probably this line here, go all the way over. Well, it looks like it's in between 5 and 6, so not super convenient. So what we can do some math. We love math. Physics is basically just math, but like better. Alright, so we know from this problem right here, we are looking for the time, so that's our unknown variable. How long, what is the time at which the ball reaches 22 meters per second? Alright, and we know that our equation is v. What did I do over here? That's not right. It should be time. I'm sorry, I don't know why I did that. It's past my bedtime. It's 9:22. I'm up way too late. I'm sorry, I'm making mistakes. I'm getting sloppy. I apologize for the confusion. Yeah, so this is t because that's your x. The x, see here, x. This is your x-axis, so that should be t. Alright, so v is equal to 3.07 t plus 4.15. Okay, so if we take this v, plug it in there, we can solve for this t. Okay, so 22 meters per second equals to 3.07 meters per second squared times t plus 4.15 meters per second. Okay, and if you're wondering, I'm going to be using the units now because the cat's out of the bag. What we're actually working with. Here's the units right here that I'm working with: meters per second, or meters per second squared, and 4.15 meters per second. I'm going to be showing you how to do it with the units. You don't need to use the units, you can just use numbers, but I'm just going to be modeling the proper use just so that way you see it. Okay, so first step, we need to get t by itself. We have this extraneous 4.15 here by itself. We need to get rid of that. Come on now. So let's get rid of it. 4.15 meters per second. Subtraction on both sides. Well, that's very convenient that we can subtract, that they have the same units. That way we can subtract them. It's crazy how that happens sometimes. That's always going to happen. All right, so let's take 22 minus 4.15. 17.85. 17.85 meters per second is equal to 3.07 meters per second squared times t. Okay, we need to get t by itself, get rid of this. To do that, we do the opposite. We're multiplying, so we're going to divide because that's the opposite. 3.07 meters per second squared. That cancels with that. I have to do the same thing over here. Okay, so we have meters on top and on bottom, so the meters cancel. We have 1 second up here, and that's going to cancel with one of them here, but it leaves one behind. Okay, so let's take 17.85 divided by 3.07. That gives us 5.81. Okay, 5.814. You know, break that off, round. Okay, so that's just going to leave you with 5.81. All right. And if you're following along with the units part, basically we have a unit that would look something like this. But because of algebra rules, when you have a fraction, when you have something at the bottom of a fraction, it flips up to the top. So don't worry about all this. The unit stuff is much more difficult than the numbers. Focus on the numbers. This equals t. So 5.81 seconds is our time. You're not being tested on the unit analysis part of this. Just that you can get the final numerical answer and put the final target units with that answer. So this is called unit analysis. All this extra math that I did with the units, you're not tested on that. Don't worry about that. I have to show it to you and expose it to you, and as we move on, like, that will make more sense to you. I know it looks complicated. It's actually quite easy, but I'm just showing it to you now. I don't expect you to do it. So just focus on the numbers that I'm using, and know that at the end you have a target. Like, if you can identify, I'm trying to measure time here, or I'm trying to calculate time, so I need to match it with the time unit, and you put that at the end for your answer, you're good. Okay, so just your final answer is what I'm actually going to grade. Don't worry about the unit analysis. I'm just going to be doing it just to model it. Okay, so next we're looking for the speed of the ball after 6.25 seconds. All right. How about, let's use purple this time. So I want to know the velocity. But this time I know that I'm given 6.25 seconds. Okay, our equation is velocity is equal to 3.07 v plus 4.15. Keep forgetting that one. Okay. And I forgot my units. Can't forget my units. But you guys can. Maybe I just shouldn't even show it with the units because it would just confuse you. But this is the proper thing, so I'm just going to show you the proper thing. It'll be fine. Okay. We're going to take this time, plug it in over here, right there. Alright. So rewrite this equation with the new number in there, 3.07 meters per second squared times 6.25 seconds plus 4.15 meters per second. Okay, so we're going to multiply. We can't add these things because they have different units, meters per second and seconds. So we need to multiply these together. Okay, so when we multiply these, we're going to get, what is it? 3.07 and 6.25. 6.25 times 3.07, 19.1875. Okay, and since we put when you multiply units together, they just kind of sit together. So meters times seconds divided by seconds squared, plus 4.15 meters per second. Just FYI, what I have right here, yeah, there we go. Just with this setup, if you had like x squared over x, one of these x's would cancel out with those, and that would just simplify to x. Similarly, if you have x divided by x squared, this x cancels with one of those x's, and that would be 1 over x. So understanding that principle, this seconds cancels out with one of the seconds here, leaving us just with 19.1875 meters over seconds plus 4.15. So on your paper, if you're not paying attention to the units, you wouldn't, like, you can add these two numbers together after you multiply, but that's actually just following the order of operations, and it works out that way anyway. So it doesn't actually change anything here. It just kind of explains why you can add these two numbers. That's unit analysis. Just, it doesn't really change anything. It's just explaining why things happen at a deeper level. So anyway, let's add these numbers together. 19.1875. And remember, I don't round because this is not a final answer yet. You only round final answers. We're going to add that to 4.15. We got 22.3375. 22.3375. Okay, equals V. This is meters per second because we're solving for V. But wait a second, that's way too many significant figures. So 1, 2, 3 significant figures, cut it off there, round that 3 into that 3. That's not going to change anything. So 22.3 meters per second. Boom. What is the ball's starting speed when t equals 0? It's right there. At time is 0, right there. That's so. If you've taken algebra, you'll probably be familiar with this idea already. Oh my goodness. That was a horrendous line. Okay. Why? Why can't I change you? No. Oh wait, I don't have a touch screen. Oh, I did it. I don't know how I did it. Oh, that's how I did it. That's crazy. Okay. Okay. So if you've taken algebra, this concept will be familiar to you. Okay. So let's say that we have this function like this. Oh, wait, you know what? I can still use this. Okay. Okay. So I have this line here on my graph. So this line is denoted by, or described by, the equation y equals mx plus b. Y is this letter is denoted by the y value at any given point. Okay, so this y value would be equal to the slope of the line times this x value plus the intercept, or letter B. The intercept, letter B, y-intercept, is where the line hits the y-axis, aka where x equals 0. Okay, so you'll notice that it hits the y-axis right here. This is the B. This thing right here is that B. So whatever the value is at this point, that is the y-intercept. Okay, so that's, and you also notice that that will always be at the 0 for the x. That's like right at that center point, that center line. So that's where that is. Okay, and that's kind of generally, just visually, that's what the y-intercept is. So if we come over here, they actually give you the answer to that. The answer is just that final number there. So when is t equals 0, what is the number? It's that. It's 4.15. And it has the same units as the y values. Okay, how much did its speed integrate? How much does its speed increase each second? That's literally, in this case, because we're measuring time in seconds, the slope, that's just the slope. So 3.07 meters per second. As time increases, speed increases. Yeah. Yeah. Okay. All right. We got another one here. Ooh, it's a an exponential function here. Where's that a log? It's not. I mean, no, it's not a log. I'm not that good at math. All right, dependent variable. That is volume. Its symbol. Oh, I can't spell, or I can't read. It's past my bedtime. Volume is symbol is capital V. The units are meters cubed. Independent variable is the x-axis. That is pressure. Symbol is capital P. Units are K, capital PA, kilopascals. The equation for this line is a power curve. Oh, that's what's called. It's a power curve. With a coefficient of 2.71. A coefficient is the number that goes before a variable. The exponent is negative 1.00. the thing for this curve, so remember we go y equals mx plus b. We're replacing y with v is equal to 2.71 pressure to the power of negative 1.00. What is the volume of the balloon when the pressure is that? Okay, so back to our drawing board. So V equals 2.71 P to the power of negative 1.00. So if we have a pressure of 1.16 kPa, we're going to put that up there, rewrite the equation. V equals 2.71 times 1.16 kPa to the power of negative 1. 1.16 to the power of, I guess we use that for negative 1, times 2.71. Okay, so that gives us a volume of 2.336 some 2.336 some. Well, we're going to cut off there, round, so it becomes 2.34. Well, we're measuring volume, so that's going to be meters cubed. Okay, what is the pressure on the balloon when its volume is 2.2? Okay, same equation, except this time our volume is 2.2 meters cubed, so that goes up there. Alright, so 2.2 meters cubed. I'm just not even gonna bother with that right now. So 2.2 is equal to 2.71 P to the power of negative 1. So, okay, here's what we're going to do. You're going to, sorry, I had to think about like order of operations real quick. So in algebra, and how to explain this, in algebra, when you're solving a formula like this and you have different things, have you ever heard of like, please excuse my dear Aunt Sally? PEMDAS, so parentheses, exponent, multiply, divide, add, subtract. When you're solving algebra, you do it in reverse. Okay, you do it the other way. So we're not going to use the exponent first. We're going to divide first. These two things are being multiplied together. To get rid of it, get p by itself, we need to divide on both sides. Okay, 2.2 divided by 2.71. Okay, and that gives us 8.11808. $811,808. Cool. And that is equal to p to the negative first. Okay, so we have this exponent. Just for reference, so that way you know what I'm about to do here. X to the negative first can be rewritten as 1 over x. So if I have p to the negative first, I can rewrite that as 1 over p. But if I flip the p like this, I have to do that to everything, okay? So I am going to flip this p because right now it's written like this. Like, okay, so if let me just rewrite this. So p to the negative first can be rewritten as 1 over p. But we don't want that. We want p on top. So if I flip p to go up top here, I have to take this, which there's an implied over 1. I have to take this and flip this as well. So my actual thing, the actual answer would be p equals 1 over 0.811808. What is that? I don't know. We got to figure that out. So basically take this. There's usually a button. Inverse. Nope. Wrong inverse. Okay. So we're going to take 1 divided by. Where's the answer? Answer. And that gives us 1.23. That's a really nice answer. 1.23 kilopascals. Okay, as pressure decreases, so as we go from 1.2 down to 0.6, the volume is increasing. Yeah, that makes sense. Bruh. Oh, I didn't hit mark. There we go. Oh, dude, what? Oh, let's check my math there, bud. Alright, hang on. Let's just redo this problem. Alright. We need to find velocity. Which is equal to 3.07 t plus 4.15. Alright. We're going to plug in t, which is 6.25. Okay. V equals 3.07 times 6.25 plus 4.15. Okay. 3.07 times 6.25. Whoa. How do I get rid of that? Nope, that's not it either. 19.1875. That sounds familiar. Plus 4.15. 23.3. That's my issue. I typed it in wrong. It's always the simple things, isn't it? I'm a silly goose. Alright, well there we go.